Hello and welcome to this webinar organized by NextGeos. My name is Bente Liljaby and I will be your host the next hour. We are going to talk about disaster risk reduction. We will learn about historical landslide data. We will learn about the modern radar technology that enables us to observe Earth from space. And we will learn about a pilot in the NextGeos project where we will improve our ability to reduce risk related to disaster. So with me today, I have a very impressive panel of experts. And I think we will just go around the table and introduce them. So we will start with our NextGeos coordinator, Nuno. Can you give a short presentation of who you are?
Hello, everyone. So my name is Nuno Catarino. I'm head of data systems at Demos. Demos is an Earth observation and satellite business private company, which is, as Bente said, leading the project, coordinating the project with funding from the European Commission.
Hello, Nuno. And then we go to you, Elefthea. Can you introduce yourself?
Yes. Hello, everybody. I am an engineer and geologist. My name is Eleftheria Poyadzi. I work in the Institute of Geology and Mineral Exploration in Greece. It's the Geological Survey of Greece. And I am also the deputy chair of Earth Observation and Geohazards expert team of Eurogeosurveys. Thank you.
Hello, we are looking forward to hear about landslides. And then we go to, we stay in Greece and we go to Ioannis.
Hello, good afternoon. My name is Ioannis Papoutsis. I am a researcher in the National Observatory of Athens in the Institute of Astronomy, Astrophysics, Space Applications and Remote Sensing. I have a background in electrical engineering and my PhD was on satellite interferometry applications. I have been the technical manager for several European Commission and European Space Agency projects on disaster risk reduction and disaster risk management, including the Lenker and Safer projects, if you are familiar with them, and of course Copernicus Emergency Management Service. And in the National Observatory of Athens, I am the chief scientist responsible for GeoHub, which provides a portfolio of services for geohazards monitoring using satellite interferometry technologies.
Hello. And then Anestis, we still stay in Greece?
Yeah, hello also from my side. My name is Anestis Tripitsidis, Research Associate in National Observatory of Athens, under the supervision of Dr. Haris Kondoes, who is the Research Director of the same institute that Yannis also mentioned previously, the Institute for Astronomy, Astrophysics, Space Application and Remote Sensing, one of the three institutes of the National Observatory of Athens. My background is in engineering and my master's was on geoinformatics. My colleague Ioannis during his presentation will further inform you about our institute. And for the next year's projects, for NOAA's responsibility, I am the main contact person for all the activities.
Yes, thank you. And we do have another speaker, Dag Anders Mollestad, but he has some internet connection problems. He's working on solving it, so we will introduce Dag Anders a little bit later. But before I give the floor to you, Nuno, who will introduce NextGeos project to us all, I will just do some housekeeping. We have a chat room here where you can ask questions during the presentations. We will try to answer some of them in between the presentations, or if not, depending on how tight we are on the time schedule, we will answer some questions towards the end. So please do write the questions in the chat box And Anestis and I, we will have a look out and pick up the questions so you can ask them directly to the expert. So then, yes, and yes, I think we start with you now, Nuno.
Good. So I'll let me share my screen. So I have a few slides in this presentation. Just go over a few of them and give you an overall view of what NextGeos is. So NextGeos is the European data hub for GEOS, for GEOS information system. In the context of NextGeos is, of course, the Earth observation area where we gather information from satellite data and from in situ data towards the creation of value-adding systems. So the NextGeos is a project part of the European Commission's H2020 calls. So it was in response to a call, in 2016, and we're a total of a consortium of 27 partners that will pursue the goals of the project for 3.5 years with a total budget of 10 million. The concept is to provide access to data and cloud resources seamlessly so that the users can create their own geo-related applications based on Earth observation data. A strong focus of NextGeos is, of course, the engaging of communities, data provider communities, and also the application builders. So the background of NextGeos is the increasing amount of data and increasing amount of data in Earth observation in general, which is generically called big data, and the higher complexity or the high complexity of the treatment of Earth observation images, but also the huge potential of the information that can be extracted here. So this led us to do a project that connects with the Copernicus data sources, which are the major data sources for Earth observation data, with the Copernicus core services, so the land monitoring service, the marine, the atmosphere, emergency, climate, and security, and bases our offer in what is called a big data platform for Earth observation, which is a concept that has been worked with together with ESA, with the European Commission, with ARS, the European Association of Remote Sensing Companies. So this concept of platform for big data has been inherited from other fields of IT, and it basically, you have here the ARS depiction of this concept, which is basically to have an infrastructure layer connected with resources, and then to have a set of tools and services on top that can be then provided to the final users. If you're familiar with GEO, so GEO has a very particular goal, in particular to use Earth observation towards the sustainability, the major sustainability issues of society. So NextGeos, the way it stands within the GEO communities, within the regional approach of GEO, it's a European regional approach, and it connects to the European GEO community, providing the necessary knowledge, expertise, resources, and platform and access to data that the community needs, and then it connects to European data sources such as Copernicus, Copernicus DS, and also the GCI for additional data sources. So we're sort of let's say, a broker of services, of data, of knowledge and expertise that aims to facilitate the creation of geo-related activities in Europe and for Europe. We are, of course, connected with the other initiatives, the other regional initiatives, such as the MARIGEOS, AFRIGEOS, and AOGEOS. So we coordinate our activities with them as well. So our objectives are to engage, deliver, and advocate. So to engage communities, to deliver a data hub, data and processing hub, and to advocate for the use of GEOs as a sustainable European approach for EO distribution and exploitation. I will go very fast, very quickly on the roles of the partners. So as I said, we have 27 partners in the consortium. Demos, DLR, NOAA, they each have specific roles. So some of them are more technological roles, and then others are more related to the deployment of pilot activities in the project. You will then have the presentation available and will be able to browse over the pilots and the roles. So what I'd like to focus now is on the role of the pilots. So within next years, one of the main activities, or two of the main activities, are the pilots, the innovation pilots and the business pilots. So these pilots serve as geo-related activities by themselves. So in agricultural monitoring, biodiversity, disaster risk reduction, energy, smart cities. So in several areas that are the focus of geo, but they also are used as validators of the system. So they provide us the feedback and provide in turn the usage of the system and the requirements for the further evolution of the system. So GEO, as the next years, will have several events about the project. In the slides, you'll be able to check a bit more details on the pilots and on the project timeline. Just like to say that the project has started in December, and we have a 6-month release schedule. So every 6 months we do a first release. We do a new release of the system from the requirements that we have and the developments that we've been gathering. So the first release was now in June. It was restricted to the project pilots, and we're aiming for a December release for a beta version for a system open to a community. So please stay in touch and have a good webinar.
Yeah, thank you, Nuno. Can you turn the screen share back to video so we see each other? And like Nuno said, we have like Nuno said, we have several events going on in the coming days, actually, and the coming month. But right now, just to mention that this webinar is actually part of something we call the User Feedback Week. And we are addressing user feedback and on the case of a disaster risk reduction. So we are using one of the pilots as the theme for a series of outreach activities. So we have this webinar, we have podcasts coming out this week, we have meetings, and we will also have live broadcasts. And you will get more information about this on our webpage, nextgeos.eu, where you will find also the presentations after this webinar. So now we are going to hear about some natural hazards, some landslides, and some exciting data that you have in Greece. Eleftheria, the floor is yours.
Hello, I'm trying to share my screen. Let's see.
Looks promising. There's a lag, always a lag. And we see your presentation.
That's good. That's good. Let's begin then.
Yes.
Okay. So in this presentation, we will speak about the Institute of Geology and Mineral Exploration and what is the role of Engineering Geology Department. Also, we will speak about the landslide database we have. And finally, we will see what we can achieve using both ground and satellite data. The Institute of Geology and Mineral Exploration is the National Geological Survey of Greece. It is dating back to the 1930s. IGME is the scientific advisor on geoscientific issues. Engineering Geology Department deals with geohazards, doing all sorts of related studies to support large engineering works or to help mitigating the impacts from the geohazards. A department keeps a landslide database. Here we can see in this slide the information recorded. It is related to lithology. Also, there are data related to the times, the type of the landslide, or what caused the triggering factor. Here we can see the pilot area we have selected for this, and the blue dots are the landslides that are being recorded in the database, while the red ones are the years, 2015 and 2016. All events recorded in the database derive from scientific reports that have been elaborated by the geologists of our department all these years. The oldest report in our library is dated on 28th of April in 19. There are different levels of detail. That's why we have three different ways to present the landslide. We have points, lines, and polygons. All reports are the result of fieldwork, but the detail depends on available base maps, on the date of the recording, or of the screen. It is worth mentioning that usually we perform in situ investigations on landslides that had an impact on people, on structures, or on networks and lifelines. That most of recorded events are concentrated in urban areas and along networks. In the following, we can understand variability of data. We have projects with different scope and time-dependent scale. We have some reports, the older reports, usually provide the description of the location without a map. That is why we record these events in our database as points, to point out that very sure where the exact location is. Also, there are some reports that have been elaborated during the response landslide team. What happens when a serious landslide happens? We go in situ, usually in the first 28 hours, to give the first instructions. The result, it is a recording that, like the one we see in your screen, which gives good information on location and type of event, but give a detailed map of geological formations. This is another example. It is an example of more detailed maps. We do them in the frame of geological studies for housing suitability. This is for urban areas, and they are done in order to, they are in scale 1 to 5,000 to 1 to 1,000. Finally, in specific areas, we have performed engineering geological maps in scale 1 to 25,000. Here there are geological formations. In the legend, they describe their geomechanical behavior. And of course, we have many landslides recorded. Here you can see they are recorded as polygons. Let's see now what can we do to merge ground and satellite data. At the left side, we see an inventory map from the database. And at the right side, we see polygons derived from digitization using optical means. This helps at the next steps to find susceptibility and hazard. Another field that we can cooperate is at the level of a village or even at the level of houses. Here you can see a village that belongs to the pilot area. It's at the south part of our pilot area. And here we have creep. Creep is a long landslide. Here you can see many cracks on buildings and on roads. In these maps, we have recorded the cracks. You can identify that the cracks are in two separate areas. What the radar interferometry can help us here is to identify the failure mechanics. This image will be derived from either two separate landslides that are mostly shallow, or one bigger, deeper landslide. To see what exactly it is good to have a monitoring. Monitoring in situ is expensive, and also you cannot have it at the time when the cracks derive. Interferometry is the best solution for this. If we see in between some movements also, then we would assume that it is a grand landslide, and we take more serious measurements to stabilize the area. These were some thoughts for cooperation. Thank you for your attention.
Thank you so much. That was really interesting. I have a question before we go on. The next one is Dag Anders, who can prepare himself. There was a lot of data, and do you have? And you talked some. You had some villages and local communities there. Do they trust the information that you provide, the observations that you do? Or is it a difference between what you do locally or what the information you get from satellites? Have you made any experiences with that?
Sorry, but I don't know if you hear me. Do you hear me?
Yes.
Yes. I missed the question. Sorry.
So, do you experience that people are trusting the data you are collecting on ground, or is it a difference between the data provided by satellites and what you are doing on ground for the local authorities, for the local people?
Well, I think that both data are useful. Yes, of course, we must go in situ because people are waiting for us, are waiting for the first instructions. And also there are kind of things that you cannot see from satellite. But satellites also are very useful for other things like the one I have described. People trust us and they trust also any other research we're doing either in situ or satellite.
Okay. Thank you, Dag Anders. I see that you are attempting to to show a presentation. How are you doing? Can you hear us? It seems like that's not the case. We lost Dag Anders again. He's coming back.
Okay. Shall I try to share it again then?
Yeah, but before you do that, Dag Anders, we didn't actually meet you
yet.
So can you please introduce yourself and tell you who you are and what you do?
Yeah, I'm Dag Anders Mollestad at the Norwegian Space Center. I'm the Norwegian delegate in the Copernicus committee. I'm also delegate to something new called ESA Incube, the innovation program for the European Space Agency in the Earth observation domain. And I would try to talk a little bit about how we exploit interferometry INSAR in Norway.
Excellent. Okay, so we cross our fingers and try to do a screen share.
Yeah, then I'll try it again.
Yes, please. There's always a time lag. Looks promising.
Okay. I'll go on from here. You see the first page?
Yes, we do. We do see it.
Okay. Yeah, then I just go along. Yeah, I think I'll go right ahead to the first slide here. And yes, we have been using interferometry in Norway for quite a long time. Interferometry is, as you know, when you have subsidence on the ground, the radar wave from the satellite will go a little bit longer, and based on how much longer it goes, you can take out height information. And this is what we have done here in a mountainside in Norway, which is quite, it can be dangerous when it goes off. And it's also been made a movie about that that recently was launched. In this picture, you can see that the biggest movement here is up to 1.5 centimeters per year. And we have earlier seen, for instance, in 1905 and 1936 in Lodal, that you had incidents when the mountain went off and you got a tsunami, and then there were casualties of I think 61 persons in 1905 and 79 persons in 1936. So it's a very important field for Norway to follow these mountains. And what we have been seeing when we began using Radarsat for the western part of Norway and northern Norway, like we are seeing here. When we began to study this, we found much more mountains that were on the move than we knew from earlier. And here you can see an area in northern Norway. Everything that is in red is moving, and the more red it is, the more it moves. And I think the places where you have the largest movement in here is up to 15 centimeters per year. So it's important to follow this. And that has been sort of the reasoning, the promising results here, that we are now making for the first time an operational system that will measure the whole of Norway with this technique, and that is both with respect to landslides and also with respect to infrastructure. And I will continue with infrastructure. This is from the Oslo City Center. It's some of the first results from Sentinel-1. You see the Opera House, the white big house there, and you see also one red dot. It's mostly green, but you have one red dot, and then you see the images to the right, where you see the movements relative to the red dots that correspond to approximately 1.3 centimeters per year. You can also see the Oslo Central Station, where you have red movements, and you have also a new development there south of the Central Station, where you have the barcode facility. And this barcode facility is not, which is new buildings, are not moving so much, but you have movements close to the barcode. We have earlier seen, this is some years ago, we studied this area. It's from its average measurements from Radarsat for 3 years between 2010 and 2013, and this is quite close to where I'm giving this presentation from, our facilities at Skøyen in Norway. And when I walked around in the neighborhood, I could go into a parking house and find a crack in the parking house based on these interferometry measurements that were done with the satellite approximately 800 kilometers above the ground. So that's amazing, I think, and which shows the great potential of this technique. And that's why we made this, or started making this Norwegian Center for Deformation Mapping. We started the development last year. It's a collaboration between the Norwegian Space Center, the Geological Survey of Norway, the Norwegian Water Resources and Energy Directorate. Both of these are responsible for landslides and the monitoring and mapping of those in Norway. Then we have subcontractors, the Research Institute Norut and the PPO labs in Holland. And the goal with this project is to make operational INSAR subsidence data available over the whole of Norway and have a production line for this, and to improve the accessibility of these results for both public and commercial users. And the main topics is mapping and risk management of geohazards and rock slides, but also subsidence related to infrastructure. And we see this as a tool for creating downstream use in geotechnical, climate, big data analysis, insurance, property market, structural engineering, and transport applications. And to the right, you can see a little bit about the production line. What we will make freely available is based on Radarsat and Sentinel, and if we see that we have very dangerous areas, then it's relevant to go in with TerraSAR or Cosmos SkyMed. And we download satellite data, we store them, we do interferometric processing, and then we have are making system for making this data accessible. And the main public end users will be, in addition to the two mentioned earlier, the road authorities and the railway authorities. A little bit more detail. This means that we now will get subsidence time series of 1 billion measurement point locations in Norway. That's a lot of data. So this can, in theory, be updated every 6 days. So 1 billion new measurements every 6 days, and that means that it's not easy to be an operator anymore, because it's a lot of data and you need to have big data analysis tool. The system is based on 4,000 Sentinel-1 products per year. We get data from our own Norwegian collaborative ground segment. We have invested in a high performance cluster for INSAR with 500 central processing units, 10 terabytes of RAM and 1.5 petabytes of storage. And this is corresponding to 1/6 of the public data catalog of Google Earth engine. So it's big. We think that it's important to make it operational, truly operational, that you have data flowing all the time and making nationwide. And in order to do that, we need to extend and enhance the state of the art of also the R&D to able to have the different slices of INSAR images put together, and also do something we call dynamic INSAR processing, that you don't have to start from scratch every time when you get new data. And we will have a free and open data policy with full resolution based on the Sentinel-1 images. And to the right, you can see the first INSAR mean coherence map. We have also results for southern Norway, but I'm not showing this here. And this is the development. It has taken a long time. We had the first, we started already in 2001, 2005 with pilot studies, and then it was more with ERS, but it really, the real start of it, big time, I would say, was from 2009, where we started to get quite a lot of RadarSat images. And that was a huge advantage when we started with the Sentinel-1H, because we had then a lot of experience both with algorithms and also with the big scale use of interferometry. So now we are scaling up, and in the future, this will be a nationwide operational service with semi-automatic processing and dynamic updates. We are extremely happy with the quality of the INSAR subsidence measurements. Here you can see both RadarSat measurements and Sentinel-1 measurements for two locations in a mountain called Gammanjoni. That is one of the mountains where we have found the movements from satellite data. You can see on reference point 2, you have which is the upper part here, where you have gray measurement points from RadarSat, and then you have red and more often updates with the Sentinel-1, and you can see how nicely they are put online. And also with the reference 1 point, where you have light blue from RadarSat and you have dark blue from Sentinel-1. So we have seen that if you have inaccuracies with the GPS measurements, for instance, we can also use the INSAR measurements to calibrate the GPS when you have atmospheric problems and so on. So it's really amazing to see how high the quality is of these measurements. Then we are discussing with the road authorities about how to exploit it with them also, and we think that live phase monitoring with INSAR of new large building projects of transport infrastructure makes a lot of sense. If we are able to do this before they build, then we can maybe adjust the optimum path of the road, so it will be less expensive maintenance of the road. During building, it's important, for instance, if you dig a tunnel and you have houses on top of it, did the houses move before the tunnel was built, or is that something that is released due to the making of the tunnel? And that means something about giving money back to house owners that have problems due to development. And then after building, you can also see how the structure is stabilizing and how it develops. And also, if you have certain problems, some places you need to do maintenance on those places and maybe do more accurate measurements also on the ground and more detailed and often. We have also the last years been looking a lot into how many INSAR measurement points are needed to characterize subsidence of infrastructure. Here you see a red rectangle of approximately 60 times 100 meter. And you see that with ERS, you had only 15 points on this, shall we say, narrow football field. That is one football team with 4 substitutes. And the ERS was, as you probably know, had 5 times 25 meter resolution for the starting point of the radar pixels. Then with the RadarSat 2, that the mode that we have used the most there has also been 5 times 25 meter, but there we have been able to get out 60 points, corresponding to 5 football teams on the ground with 5 substitutes. And then when we went up to 3 times 3 meter with Cosmos SkyMed, then you have 330 points, corresponding to 30 football teams on this tiny red rectangle. And then with TerraSat X, the best resolution that you can get from that, which is 25 times 100 centimeters, then we get 8,000 points, corresponding to that every square meter and more than that is covered with an INSAR subsidence measurement. And of course, this is dependent on the ground underneath, how good the scatter properties of the ground is. But this is, let's say, a general or an example of how it can be in an urban area. And we see that the PSI permanent scatter interferometry technique is very, very promising, and we think that this also may be used more in the let's say more rural areas for landslides, in addition to the urban areas. Then we are also working a lot with how to present this in a good way for the users. Here we have shown a visualization of subsidence along the railway network in the Oslo area. The railway authorities are not interested in doing a lot of measurements or all the measurements that are far away from the railway. So we have only showed it for the railway. And I think this is also very important that you are able to show what's interesting for the specific user. This is an example from Iraq, the Mosul Dam, which shows also the capabilities of two things, I think. Both how you can monitor dams with the INSAR, and also the security and the climate issue related to dams. Here you can see that you have 5 to 10 millimeters per year movements in the center of the Mosul Dam. And of course, this is not something that if you have a flooding of the Mosul Dam, you have problems in Mosul very soon, only 30 minutes or something, and in Baghdad 2-3 days downstream of this. So INSAR is important both for climate, water, and security, I would say. Here we have an example from the San Francisco Tower, which the team that is also doing the operational production in Norway has done. It's NU Norut and PPO Labs. And here we see that San Francisco Millennium Tower is sinking with up to 5 centimeters per year. You can see the cracks in the wall to the right, and you can see the big INSAR map of the whole of or part of San Francisco with the red dots in that we have now scaled up to the left. Then another important thing is this visualization, and this is a tool that we are playing around with at the moment. We have a photo of the area as the background, then we have maps on top of that, and then we have subsidence data on top of that again. And then you can go into this tool and click on the point, and then you can get out the time series. And as you see, have been done here on one of the houses. And this is a house that I would say is quite stable. You can see that it moves some millimeter from season to season when you have a time series from 2008 to 2016. This was originally an example for a girl that had her working day at the Space Center. She was 12, 13, 14 years old or something, and I should show how INSAR worked, and this was a measurement from her house. But we are, I think, both dissemination, visualization, and big data analysis is going to be extremely important for the development of operational and applied INSAR in the future. We are also working heavily with the Commission and different nations in Europe with respect to Copernicus and a European ground motion service. We see that operational worldwide deformation mapping is for the first time made possible through Copernicus. We hope that it will be possible to save lives from geohazards worldwide in the future due to this. And we also think that it should be possible to create knowledge-based jobs, revenue, and added value for the whole of Europe and also for the whole of the world. And we are working very hard to get this European ground motion service into the Copernicus Work Program 2018. And we are at present also looking into a white paper on that one. And Norway is generally open for collaboration both in Europe and worldwide. And I think we just have to say that This is a story that has just been starting, and we are going to continue it. And I continue with a visualization of subsidence data in the neighborhood of where my family live in the western part of Norway. And you can see to the right, you have an area called Osmundneset, where it's very red. And that is an area where we also found new movements from satellite data that we didn't know from before, and where you could then go in from the ground and make it more or ensure the security for the people traveling on the road underneath. So this is what we are hoping also to do a lot of in the future, both in Norway and also in the Europe and rest of the world. So thank you. Maybe I talked a little bit too much, Bente.
I think we are just a little bit over the time. Thank you so much, Dag Anders. As you heard, there are many more applications than just landslides that you can use INSAR for, that Dag Anders pointed out. And I will just, as a sort of a curiosity, I don't know if you noticed that Dag Anders, he showed some INSAR movement images from San Francisco. And not very long after those observations were made, I did some really in situ observations there myself, the American Geophysical Union. So the satellite images are through. Yes. And now we will hear more. Now we will go into how we can combine this satellite capacity that we have with the INSAR that Copernicus is providing, and couple that with the data that is done on historical data that we heard of earlier. So, Ioannis, are you ready to tell us about the pilot, the disaster risk reduction pilot of next year?
So sure, thank Bente. Let me turn on the screen.
We can see your presentation.
Okay, that's great. So this presentation aims at providing you with a brief introduction of the next year's pilot on disaster risk reduction. And I will try to highlight our many motivation behind selecting this use case, specifically to showcase the strengths of next year's technologies and present you the tools and the methods we employ and the expected impact on two key communities for us, which is the remote sensing community on the one hand and the end user community like Eleftheria that gave a presentation before. So this is the outline of the presentation. I will start by saying a few words about my organization, its mission and some highlights of its main research activities. Then I will go straight to the rationale of the, sorry? Okay. I think I got out of presenting mode. Then I will go straight to the rationale of the disaster risk reduction pilot, its objectives and its workflow, and conclude with an example to provide you with a better understanding of the pilot. So, briefly, the National Observatory is one of the, or actually is the oldest research foundation in Greece, and our national mandate is to conduct innovative research for natural disaster monitoring and provide actionable information to decision makers and national stakeholders. Our institute, the Institute of Astronomy, Astrophysics, Space Applications and Remote Sensing, focuses on delivering disaster-related products using Earth observation. Now, our focus is mainly on emergency management services, including natural and man-made hazards, and just some indicative projects that we have been engaged with have first Beyond, which is a center of excellence that is established here at the National Observatory of Athens, and it was established in the context of a capacity building fund we received from the European Commission. And its mission is to develop a set of services based on for Earth observation based monitoring of natural disaster, with a focus on southeastern Mediterranean. We are also operating one of the European Space Agency nodes for the distribution of Copernicus Sentinel satellite imagery to specific international users such as NASA, and this is the international hub for those of you that are familiar with that. We are also hosting the Hellenic Sentinel Data Hub for the distribution of Sentinel products to all users with a regional focus in Southeast Europe. We're also participating in the Copernicus Emergency Management Services and specifically to the risk and recovery part. And very recently, we've been awarded the EFIS contract as well. We have also developed FireHub, which is a platform for Earth observation-based management of forest fires using, of course, Earth observation. And it was awarded the first prize in 2014 in the Copernicus Master Competition. And finally, we coordinate GeoCradle, which is an Horizon 2020 project, which brings together key players from the Balkans, the Middle East, and North Africa, representing the entire Earth observation value-adding chain. The project's main objective is to establish a multi-regional coordination network that promotes the uptake of Earth observation services in the region, supports the effective integration of existing Earth observation capacities, facilitates the networking and engagement of Earth observation stakeholders in the region, and enhances the stakeholder participation and contribution to the implementation of GEOS and Copernicus, again in the same region. Now let's move to the specifics of the disaster risk reduction pilot. Its main theme is landslides, where we provide an enhanced landslide risk assessment framework based on the analysis of long-time series of satellite information using satellite interferometry, as Doug Anders discussed before. So our focus here is to use similar tools as Doug Anders discussed: satellite interferometry, time persistent scattering interferometry, and combining this with other data sets for landslide susceptibility mapping. The enablers of this pilot are mainly two. On the one hand, we have some access to unique data sets from a single access point, and this will be primarily the next GEOS point of reference, let's say. We'll use satellite data, ERS, NUSAT, and Sentinel, geospatial data like land use, land cover products, digital elevation models, and other geological information, and in situ information like the landslide inventory product that Eleftheria showed before. The second driver is the distributed processing of satellite imagery using persistent scattering interferometry and using resources from NextGeos, processing resources. Now, the pilot targets to provide products related to landslides to end users and stakeholders, and we are discussing about the pilot area in Greece. And it will offer capabilities to query, visualize, and access relevant products, and deliver a robust and transferable solution for dynamic mapping and monitoring of landslide hazard zones in a complex geo-environmental setting like the one in Greece. Now, this is the pilot workflow. I know it looks a little bit complex, and I will go through this slide. We have three pillars. We have the data tier, where all the input data are stored and where we will use them. It consists of archived satellite imagery, ERS and NSAT data, static geospatial layers such as digital elevation models, land use, land cover, fault information about the faults, the lithology of the area of interest, and so on and so forth, and some dynamic data, and we will use Sentinel data and meteorological data sets. Next, we have the modeling tier, where these data sources are combined, are analyzed, and finally we have the products tier, where we deliver the products to the end user. So the concept is the following. Firstly, we analyze the historical synthetic aperture radar data to generate ground velocities, and we'll do this using ERS and NSAT data. Then we'll use these velocities as indicators for slope instability, and Doug Anders saw an example in his presentation before. And under certain conditions, you can use these velocities to update the landslide inventory dataset that we get from our end user. Then we make a statistical analysis to correlate the landslide triggering factors, these static geospatial layers, with the observed and inventoried landslides. Now, this process has as an outcome a model that weighs the different triggering factors to produce a regional landslide susceptibility product. And this process is performed only once for every region of interest. And then we move to the dynamic part of the service, where we process Sentinel-1 imagery to update the inventory and fine-tune the landslide susceptibility index. And then we use meteorological forecast to generate a dynamic landslide susceptibility product towards setting up an early warning system. Now, let's see an example to make this a little bit more intuitive. A scenario would be that a forecast alert is issued for an upcoming heavy rain, which can trigger the update of the landslide susceptibility with the detection of possible vulnerable areas based on this forecast and also on ground deformation time series based on Sentinel-1 data. Now, this is the process of updating the landslide susceptibility index. Notice that the dynamic data here are the Sentinel data, are the weather forecast data. We can also have the landslide inventory that is updated from in situ observations, and this will be done by the end user. And also we can have even the static geospatial areas can be dynamic in terms of updating the land use land cover after a severe forest fire. Which is an important parameter for landslides. Now, this is an example of a landslide inventory. Eleftheria showed you some examples before. We use these points, and we also use the other geospatial information like geology, elevation, slope, the aspect, and the curvature for the same region of interest. And we also use the persistent scattering interferometry to derive ground velocities. This is measurements spanning 2 decades, from 1992 to 2000, and from 2002 to 2010. And we can use this information now to detect new landslides and update the inventory that we have received from IRME, for example. Here we overlay ground velocities with in-field observation, and we can use this info on the one hand to confirm existing landslides, and on the other hand to make new detections that were not recorded by the relevant authorities. And this is what a final product may look like, which is a landslide susceptibility product based on the modeling and the analysis before. Now, this is the final slide of my presentation. Why do we believe that this pilot has an impact for disaster risk reduction? Considering the remote sensing community, we will employ interferometric processing on demand using Sentinel-1 data, and this processing will be is triggered by some severe weather event alert. We accommodate the processing of Sentinel-1 time series, and this is a big data problem. It is challenging and requires distributed processing solutions to cope with that. And finally, we provide systematic observation of ground velocities and deformation histories at regional scale on a systematic basis. And this is an important database to set up. From the end user perspective, the disaster risk reduction pilot will provide an updated landslide inventory, will identify new and remote landslides not previously known, and the most important part will set up an early warning system that will be based on meteorological information and the responsive and robust processing of Sentinel-1 imagery using persistent scatter and interferometry. And this sums it up. Thank you for your attention.
Well, thank you very much, Ioannis. This was a really interesting. Do any of the panel here have questions for Ioannis? I don't know if you lost me. I asked if any of you others have questions for Ioannis. While you are thinking about that, I do have a question for Ioannis. So I think I heard that you were, I mean, the topic is landslide, and you have the historical landslide data that you combine with the INSAR data and other data. But you mentioned also that forest fires and then, of course, weather is linked to this. So do you see a potential for making this a multi-hazard warning system or a contribution to a warning system?
I would say that doing this for landslides is challenging enough, meaning that we will use the impact of other natural disasters, such as forest fires, to update a land use land cover map, which by itself is a triggering factor for landslides. So we use the effect that other disasters have on driving natural processes for landslides.
I see. And then I had another question based on an experience you have myself on combining in situ and historical data, in sea level that was, with satellite data. There's a big difference in resolution and quality of these two different types of data. Did you mention how you are solving that?
Okay, this is in fact true. So as Eleftheria said in her presentation, even the inventory is not an harmonized, the in situ inventory is not an harmonized product. It has some points, has lines, has polygons. So a first step will be to make an harmonized product and indeed identify a process to integrate this information with the results we get from persistent scatter interferometry with velocity maps. It's not a straightforward process, but it is something that we have tested before, and it works.
Terrific. And now I see that we, I think you can turn off your screen share and turn on your camera and again. And so we see you, by the way.
Okay.
Yeah, there you are.
Sorry about that.
No worries. Any other questions now that I ask some questions? Any other from the panel? Dag Anders, do you have any questions? Is there similarities or differences in the way that Greece now and this group is using INSAR data and what you are knowing about Norway? Your microphone.
Okay, now it should be on. Yeah, I think that Greece and Norway will work very well together with respect to this European ground motion service, and in this task force that has been established for that, we have also had people from Greece involved. So I think that is I had all those. There was a little bit problematic for me to see the last slides in this presentation, so I did not catch all the details in after a certain point. So that was a little bit yeah. So
yes, indeed. And if I can add, in Dag Anders' presentation was very interesting because he showed, I think, an Earth observation service, let's say, for covering multiple applications, spanning from landslides to construction monitoring, for natural process monitoring, water processes monitoring, so on and so forth. What we would like to showcase in this pilot is the fact that it's not that we produce a generic service, but we focus on landslides and we use some modeling in order to provide risk assessments for disaster risk reduction. So it is more focused on one, let's say, natural disaster, but it goes deeper in the modeling part of the physical process behind this.
Yeah, I think this is very important, and of course, the modeling and simulation in this field will be much more interesting when you get access to so many data that you are able to do now, and the understanding in geotechnics and geology should be it's a huge potential, I would say. And of course, in Norway also, I am sure that you have been in contact with John Dells at the Geological Survey in Norway at some point, and of course. Rock slides is more than landslides, is the, let's say, main user in Norway for this system. But I think as long as you're able to make an operational stream of these subsidence data available, then it can be used in very many disciplines, and I think it can develop a lot of disciplines as well. So of course you need to combine it with models. Of course you need to combine it with in situ data. You're only getting data every 6 days, which means that if you have very dangerous areas, you need to have more data more often, every second, so to say. But I think there is a great synergy between this system and such.
So Nuno, so the disaster risk reduction is one of our 10-11 pilots. Do you agree that it sounds like we might have other potential pilots that we can test on our data hub once we develop it further? Any thoughts? Your microphone.
Hello. Yes,
Yes.
I was muted. Yes, definitely. We have, as I said, 10 pilots, and we have been doing. So there are different readiness levels. The one from Norway is one of the most advanced ones, and we are now preparing for the geoplanary now in October in Washington, and there are 2 pilots which will be presented there as well. So these 2 will be one from Vito on agricultural monitoring, and one from DLR on urban environment monitoring. So these 3, let's say, would be probably the most advanced ones, together with the one from Armin on energy monitoring for solar solar panels deployment. Yeah, so I'd say these 4 are the most advanced pilots that we have so far, and for sure we'll see them fully deployed in XGEOs during next year.
Yes, but I also sort of spin-off pilot. If I listen to Dag Anders and Johannes here, that there might be some sub-pilots, so to speak, to develop their different approaches or common approaches, depending on how you see it. I don't know, Dag Anders, is that something? Would it be interesting to sort of test the NextGeo's data hub on some of the problems that you are addressing from the Norwegian perspective?
That might be. I think now it will be important for us to let's see what happens with this Copernicus European Ground Motion Service now. That is something that will be decided in the Copernicus committee, I think, at the end of the month. It will be further discussed in the Copernicus User Forum in October and so on. And it's a process that will start from, let's say, late 2018 if everything is working well. So I think that a combination of that and NextGeo's can be interesting with respect to presentation and so on. But of course, it's enormous amount of data we are talking about. So it's this Copernicus DIAS platform is also, of course, very important. So we need to take it a little bit step by step, I think.
Of course, yes. But it's good to hear that you already know about each other. Also, Eleftheria seems to know John Dells. So we have actually a community, a disaster risk reduction community here already. So I think that's it as far as I can see. If there's anything I've forgotten, please remind me, the rest of the panel. Anestis, is there something else?
No, nothing from my side.
No. So then I think we say thank you so much for those who are listening and for those who are going to listen to this and watch this webinar later on. And thank you so much, all of you in the panel. It was very interesting and a very interesting discussion we had afterwards. So bye-bye for now.
Bye.
Bye-bye.
Bye-bye.
Thank you very much. Bye-bye.
Bye bye.